In this video, we are going to work on problem 3.1.6. Let f be the function given by f of x is x if x is a rational number in the interval 0, 1, and 1 minus x if x is an irrational number in the interval 0, 1. Determine which of the following limits exist, and for those that exist, find their limits. We have to consider the limit of f of x as x approaches 1/2, and the limit of f of x as x approaches 0. And in part C, we consider the limit of f of x as x approaches 1. So before solving this problem, let me recall the definition of limit. Okay. So let f be a function defined on a domain D, and let x bar be a limit point of D. Then the limit of f of x as x approaches x bar is equal to L if for any given epsilon greater than 0, we can always find delta greater than 0, so that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus x bar is greater than 0 and less than delta, and x here is in D. Okay, so now let's go ahead and work on this problem. At first, we consider the limit of the function as x approaches 1/2. Now, when x approaches 1/2 and x is in the set of all natural number, we can see here the limit is 1/2. Okay, so x here approaches 1/2 as well. And if x approaches 1/2 and it is in the set of all irrational number, then 1 minus x approaches 1 minus 1/2, that is 1/2. So we predict that the limit of the function f as x approaches 1/2 exists. Okay, and now we are going to use the definition of limit to justify that the limit of this function f of x as x approaches 1/2 is 1/2. Okay, now for any x in the interval 0, 1, we evaluate the absolute value of f of x minus 1/2. Okay, so it depends on whether x is a rational number or an irrational number. So there are two cases. It is x, the absolute value of x minus 1/2 if x is in Q. Okay, now over here x is in the interval 0, 1 as well. And in the second case, if x is irrational, it is gonna be 1 minus x minus 1/2 if x is in the complement of Q. That means in the set of all irrational number. Okay, so observe that this is exactly the absolute value of x minus 1/2, because that is minus x plus 1/2. Okay, so this is equal to x minus 1/2. Okay, so we have seen that for whatever x in the interval 0, 1, the absolute value of f of x minus 1/2 is exactly x minus 1/2. Now, take any epsilon greater than 0. Now, in order that the absolute value of f of x minus 1/2 is less than epsilon, we only need to choose delta such that the absolute value of x minus 1/2 is less than epsilon as well. So in this situation, we're gonna choose delta equals epsilon. Then we can easily see that the absolute value of f of x minus 1/2 is less than epsilon whenever the absolute value of x minus 1/2 is less than delta and greater than 0, and x here is in the interval 0, 1. Okay, so by the definition of limit, the limit of the function f of x as x approaches 1/2 is 1/2. Now, for any x that is in the interval 0, 1, we are gonna evaluate the absolute value of f of x minus 1/2. Okay, so it depends on whether x is in the set of all rational numbers or x is in the set of all irrational numbers. So this is equal to the absolute value of x minus 1/2 if x is in Q. This is true because f of x is equal to x if x is in Q. Okay, and in the case where x is not in Q, this is equal to 1 minus x minus 1/2. Okay, so but over here 1 minus x minus 1/2 is 1/2 minus x, so it is exactly this. So in general, this is equal to the absolute value of x minus 1/2. Okay, so now we're gonna take any epsilon greater than 0. Okay, so in order that the absolute value of f of x minus 1/2 is less than epsilon, we only need to make sure that the absolute value of x minus 1/2 here is less than epsilon as well. So we can let delta be epsilon and then apply the definition of limit. Okay, so now take any epsilon greater than 0. We choose delta equals epsilon. Then from here we can see that the absolute value of f of x minus 1/2 is less than epsilon whenever the absolute value of x minus 1/2 here is less than delta and is greater than 0. And notice that x is in the interval 0, 1. Okay, so by the definition of limit, therefore, we can see that the limit of the function f of x as x approaches 1/2 is 1/2. Okay. Now we are going to focus on the second part of the problem, considering the limit of f of x as x approaches 0. Now let's look carefully at the definition of the function. F of x here is x if x is in Q, and 1 minus x if x is not in Q. X here is in the interval 0, 1. Observe that if x approaches 0 and x is in the set of all rational numbers, then f of x here is x, so it approaches 0. Okay, while if x is in the set of all irrational numbers and x approaches 0, then f of x here is 1 minus x, so it approaches 1. Okay, so we predict that the limit of f of x as x approaches 0 doesn't exist. To prove this, we are going to use the so-called sequential criterion for limit. Recall that let f be a function from D to R, and let x bar be a limit point of the domain D. Then the limit of f of x as x approaches x bar is equal to L if for any sequence xn in D not converges to x bar with this condition, xn is not equal to x bar for every n in n. We have that the limit of f of xn as n approaches infinity is L. Okay, so again we are going to use this criterion for limit in order to solve the second part of the problem. Now let Rn be a sequence of rational numbers in the interval 0, 1 such that Rn is not equal to 0 for all n in n, and the limit of Rn as n approaches infinity is equal to 0. Such a sequence Rn does exist by the density of the set of all rational numbers in the interval 0, 1. Okay, now let's look at the limit of f of Rn as n approaches infinity, because f of x is equal to x if x is in Q intersection the interval 0, 1. F of Rn is just Rn, and as you know, this limit is 0. Okay, now similarly, let Sn be a sequence of irrational numbers in the interval 0, 1. Sn is not equal to 0 for all n in n, and the limit of Sn as n approaches infinity is 0. Again, such a sequence Sn does exist by the density of the set of all irrational numbers in the interval 0, 1. Then let's look at the limit of f of Sn as n approaches infinity. Notice that f of Sn is just 1 minus Sn. And this is 1 because the limit of Sn as n approaches infinity is equal to 0. So we have found two sequences Rn and Sn such that both sequences converge to 0, and this condition is satisfied for all n in n, but the limit of Rn is 0 and the limit of Sn is equal to 1. Okay, so therefore the limit of f of x as x approaches 0 doesn't exist.